Welcome back, students. We are now going over to the second half of this course, the inferential statistics, and it begins from chapter 8, Introduction to Statistical Inferences. And then it's going to continue on toward the end of the course, as a matter of fact, as you can see in this content. It begins from chapter 8, Introduction to Inferences, chapter 9, some more inferences, chapter 10, still more inferences. From chapter 11, at least the term inferences disappeared from the chapter title, but in reality, they're all about inferences. In short, we're about to begin something that is really important: statistical inference, or inferential statistics. Now, if you ask me what it is, I don't think I can answer that in a simple sentence or two. It's just too deep. Instead, let me try to answer those questions using two aspects of it. One is the estimation theory, which will be covered by 8.1 and 8.2. And the other is hypothesis testing, 8.3, 4, and 5. Now, what is the estimation? Well, here's a nice picture that explains it, figure 8.1. From the large population, you fix a certain variable of interest and consider a certain parameter. It could be the mean height, mean weight, mean income, or anything that you can think of. Typically mean, but in some cases we can consider standard deviation or other things too. But most of the time, it's going to be the mean that we are interested in. But it's going to be very difficult to find out directly from the population. There are too many people here. It's going to be very hard to interview them all, prohibitively expensive, and so on and so forth. So what do? We take a random sample, analyze the sample data, and get sample statistics. Using the sample statistics, we do appropriate mathematical formulation, and then we are going to get appropriate estimation for the parameter value. By the way, please remember, all those numbers associated to populations are called parameters, and we use Greek letters to represent those. And all those numbers, the corresponding numbers associated to sample, are called statistics, sample statistics. And we use Roman letters like X bar, S, things like those. Here, mu and sigma, things like those. And this cyclic structure explains the idea of estimation theory. And then once you have estimation, and that becomes a standing hypothesis, and then there's going to be another estimation that's going to become an alternative hypothesis, and you have to compare those two appropriately. That's going to be the topic of 8.3, 4, and 5. In short, we're going to have multiple of these cyclic loop structure. So that's going to be a little bit higher level. In short, let's begin with easier one, estimation. Now, how do we estimate? Well, the most trivial way to estimate is to use a number. Use sample mean to estimate population mean. Use sample standard deviation to estimate population standard deviation, and so on. But if you do that, we lose all kind of accuracy, and always we do have errors and things like those. So this is not really good. So you have to consider some estimation error, give and take. Consequently, we end up with an interval. And this kind of interval is typically called confidence interval for the mean. And there are other kind of intervals too, like prediction intervals or tolerance intervals and things like those. But this is 1000 level course, so we're going to focus upon confidence levels. Here is a visualization of a confidence interval. We are predicting, or we are estimating, the sample mean mu, which we don't know, but the best estimate is the the sample mean x bar. So that's the expected value, and that goes right in the middle of this normal picture. Now, did I say 95% confidence interval? That means there's 95% of chance that the real mean falls into this interval, highlighted in blue where I'm moving my mouse around, between mu1 and mu2. This blue area is 95% or 0.95, which we call the confidence level. By symmetry, we have to have 2.5% here and 2.5% there. What if I change it into something else, like 80%? In this case, middle area will become 80%, a little smaller, so 80%. And 10% here, 10% there. So the smaller the confidence level, the smaller the confidence interval. If I increase this to, say, 98% confidence interval, what do we have? We have 98% is the blue part in the middle. Consequently, we have 99% is the blue part. So we have to have 0.5% here and 0.5% there. Let's go back to the default 95%. This kind of thing is called confidence interval. In some cases, we're interested in just one-sided confidence interval. This is particularly the case if you have some kind of safety feature or something, and if the safety feature is working exceptionally well, hey, that's okay. The worst possible case is something that we are particularly interested in and you have to test. In that case, you just look at one side. In that case, confidence interval is just from here to all the way over there, mu1 to infinity, and we are looking at only this part, which we call lower confidence bound, this mu value. And in this case, we have upper confidence bound. Those are relatively rare, but at least we can consider those. I think we have enough time to study some example here, so let's go ahead and do that. A certain college selected a random sample of 100 commuting students. So the sample size here is 100. And obtained the student's one-way commute distance. The resulting sample mean was about 10.22 miles. Okay. So this is the sample mean, which is the expected value of the real mean mu, and that goes to the center of this normal picture. Now, if you have normal picture, you need standard deviation, or more precisely speaking, standard error. Do you all remember the standard error formula from chapter 7? It is sigma over square root of n, wasn't it? In short, this was 6.0 over square root of 100, which is 0.6. And that should be the denominator of a normal picture, which looks kind of like this. Please pay particular attention to the center. That should be the expected value. And the sample mean was 10.22, so normal picture is around 10.22. The center is 10.22. Okay, how do we find this value and that value? mu1 and mu2. Well, we can find only one of them, and you can do it through z-score computation. And how do you use z-score computation? Well, middle probability is 95%, so 2.5% here and 2.5% there. And if you look at the normal table, the picture associated normal table are all to the left hand side, so it's going to be far more convenient if you look at this mu1, this value, left hand side endpoint. So how do you get that? Is it better to use z equals to x minus mu over sigma? I say no, that's not going to be very good. As a matter of fact, it can be confusing, so I'd like to discourage you from using this formula to tell the truth. Everything eventually came from this, that's true, using central limit theorem, but it can be confusing because in chapter 7, the normal picture was distributed around mu, and mu was right in the center. In this case, the center is not mu, mu is unknown, but this one x bar. So you have to switch mu and x, and that could be confusing. And then this is not just x, it will be x bar. And the denominator should be sigma over square root of n. Oh, too complicated. It's gonna be much better if you just do it graphically. We want end minus center over standard error to be equal to, or at least approximately equal to, appropriate z-score. And that's how you can find out this mu1 value, especially left-hand side value. And after that, you can find out the right-hand side value. Okay, what is the z value? Associated to 0.025 or 25%. Oh, did I say 25%? Sorry, 2.5%. Well, here is a normal table, and you can find out. This is a probability here, and that should be 25%. I'm doing it again. 2.5%, so 0.025. And you have to look up 0.025 here, but I already highlighted. It's negative 1.96. The z-score associated to 0.25 is negative 1.96. And that's how you can figure out your endpoint. Exactly how? Well, let me open up this solution and show you. Standard error, in the denominator is 0.6. We calculate it. And then n by the center of standard error is negative 1.96 for the left-hand side mu1. So by symmetry, this will be plus 1.96. So what do we have? We're plus minus 1.96. Plus or minus 1.96. Okay, so we have mu minus 10.22 over 0.6 is negative 1.96. Solving this equation, you get 9.044 approximately. And setting this one into positive 1.96, we get the second value, mu2. So from this z-score, you end up with an equation. A simple equation that you can get by flipping the denominator to the other side. And solving those, we get left-hand side and right-hand side endpoints of the confidence interval. And that's how you get 95% confidence interval. If you change it to not 95%, but 90% or 99% or 98%, you have to look up this table appropriately and get different values here in the highlighted place. 1.96 is for 95%. You're going to get different values for different confidence levels. This is my favorite way, but there may be some students who do not like to solve the equations. In that case, you can do something like this. Symbolically, flip this denominator over to the other side and then get this expression. Mu equals to x bar plus z times SE. And then SE is sigma over square root of n here, and then z-score is plus or minus 1.96. So plugging negative 1.96, we get that. Plugging in plus 1.96, we get that. Same thing, but we have two formulae in this case, this and that. So personally, I dislike this method. I prefer the first method better. But if you prefer the second method, go ahead. I'm not going to prevent you from using it. Here's the normal picture again. And then n minus center over SC formula is there too.